Okay, the purpose of this presentation is a bit of a departure from presentations that I have done regarding vehicle modules. However, we have, because of the product that we manufacture and sell, the eprom Plus programming system, we will occasionally get an inquiry about the support for bipolar proms. And in order to address that, I thought I would do this. It's not intended to, this is going to address issues with folks that work on vintage equipment, older equipment, okay, because bipolar proms are no longer used in any new designs, okay. But for people that restore and maintain arcade and video games, for people that work on industrial controls, elevator controls, things like that. One of the things about what are called embedded systems, and an embedded system is it's a processor-based, microprocessor-based product that was designed at whatever period in time it was designed. Okay, so if you go back to the mid 1970s, that's when microprocessors began to be accepted into the marketplace. Okay, and microprocessor technology was MOS, metal oxide semiconductor. You can see this as the data manual for Signetics. Signetics is no longer around. They were bought by Philips. MOS stands for metal oxide semiconductor, and bipolar means it's a different kind of technology. It's a technology that uses transistors that are fabricated from silicon, okay, and the silicon will be either what am I trying to say? For N and for P, okay. These would be, if you go back and look at transistors, there are lots of YouTube videos on transistors. You'll see there are PNP and NPN, okay, and they're all silicon, but there's silicon is an interesting element because you can do what's called doping, where you add an impurity to it, and silicon will then become charged in a certain way, where it will have a positive charge, depending upon the impurity that you dope it with, or negatively charged. Okay, and that's the fundamental, that's how transistors are fundamentally, bipolar transistors are fundamentally fabricated. All right, so given that, the bipolar transistors at the time, okay, of the original microprocessor debut with MOS technology were significantly faster, much faster, okay? So, where you had MOS transistors, which were relatively slow, okay, and by slow I mean 100, 200, 300, 400 nanoseconds, even slower than that, okay, and today's technology, we're talking about, gigahertz processors and things like that, but at the time, at that particular point in time, the MOS transistors, they weren't, operating at incredibly high speeds. However, if you fabricated an integrated circuit with bipolar technology, then it would be much, much faster, okay? One of the downsides, though, to bipolar technology was that it would consume significantly more current than an MOS part, okay? So the bipolar technology also, you couldn't make as many transistors on a silicon die as you could with MOS. Well, I don't want to belabor that, but I mean, if I'm going to do this presentation, I'll try to give you as much excuse me, background information as I can about where this technology originated and why it originated. Okay, because what would be the purpose? I mean, if you could have an MOS memory, why would you want a bipolar memory? The bipolar memory is going to consume more current. You're not going to be able to get as many transistors on a die, so why would you want it? Okay, well, the answer is speed. The bipolar memory technology was very, very fast. Okay, I'm talking about, probably 20, 30 nanoseconds compared to 200 to 300 nanoseconds. Okay, so given that, why and where did the bipolar memory components get designed? Where were they used? Okay, this is my crude attempt at art, and it's only gotten worse, it seems, as time has progressed with me. Anyway, what I want to show here is this is supposed to represent a microprocessor design from, let's say, the early 1980s. Okay, this here, the UP, which is micro P for microprocessor, is the processor. Okay, over here, the things that I've drawn, the little boxes with the circles in them, are supposed to be EPROMs. All right, EPROM, erasable programmable read-only memory. Okay, bipolar PROM, PROM, is programmable read-only memory. There is no E. Okay, and there's no E because once they're programmed, you're done. You can't erase them and reuse them. It's a one-time deal. Okay, well, why would you need it? Okay, well, I'm going to try and fundamentally go through quickly how a microprocessor works with its memory. Okay, in this case, I've drawn 4 EPROMs. Okay, the reason I have drawn 4 EPROMs is I'm going to assume that this application requires the code that was written for it is going to have to fit in not 1, not 2, not 3, but 4 EPROMs. And let's say these are 2K EPROMs. Okay, so there's an 8K program. These would be like 2716s. All right, and then up here we have a RAM chip. Okay, because microprocessors don't have any built-in RAM. RAM is where a software designer will store variables. He'll put a stack there and things like that. So you're going to have a RAM chip. RAM chips, when the power is removed, they lose their contents. EPROMs do not lose their contents. Okay, so what does this have to do with bipolar PROMs? Okay, well, EPROMs have let's just talk about what the pins are on the EPROM. Okay, the pins on an EPROM, you have what are called address lines. Okay, and the address lines select the individual byte that is stored in the EPROM, and that individual byte, once it is selected, will pass out of the data lines on the EPROM, which I've shown here. I know I didn't label them data lines because this wasn't supposed to be a course in microprocessors. The data will flow out of the EPROM and be read by the microprocessor right over here. Okay, and the thing is, you can't have, you can only read data from one EPROM at a time. Okay, so in order for an EPROM to provide its data, it has 2 lines. One is called chip select, and the other one is called output enable. Now, I didn't use output enable. As I said, I'm not trying to do a course in functionality of memory. I just want to tell you why bipolar PROMs were created and what they do. Okay, so you have these 4 EPROMs, and then you have the RAM. The RAM has address lines too, except with the RAM, data flows in and it flows out, because with EPROMs, data just flows out. Okay, so the RAM is also going to have, a chip select, an output enable, and it's also going to have a write input. Okay, but that's not relevant to what I'm trying to convey here. Okay, so we have each EPROM has a chip select line, which will allow its data to be, once it's active, be placed onto the data bus so that the microprocessor can read the code. Okay, well, when the microprocessor first starts, let's say that this is EPROM 0. This one goes, let's show you kind of an address range here. This one is going to go from 0, since it's 2716, I'm going to write it over here, 0 to 7FF. Okay, that's all the addresses, 2048 addresses, bytes that are being stored in this part. Okay, the next one is going to be from 800 to F. Okay, basically another 2048 bytes. The next one is going to be from 1000, which is FFFF plus 1, to 17FF. Okay, and the fourth one is going to be from 1800 to 1FFF. Okay, so I'm not going to map my RAM, and as I said, I'm just making this up so I can get the point across to you. So these address lines, this one, they're all going to be in parallel. All of these little lines that I've drawn here are all hooked in parallel. The thing that allows you to differentiate which EPROM is selected is the chip select line. Okay, so when the chip select line is active, then the data will flow from the EPROM onto the data bus and go into the microprocessor, and it'll be interpreted as an instruction or data or whatever, and the microprocessor will perform its whatever its program is telling it to do. Okay, well, when a designer is designing his microprocessor based system, what he needs to do is come up with some way, because what's going to happen when the microprocessor says, I want to read from address, let's just say address 0, okay? All of these lines, these are address lines coming out of the microprocessor, okay? They're going to be highs and lows depending upon what the individual address is. And in this case, this is a 16-bit address, okay? The lines are going to be a series of ones and zeros that are going to point to a specific address. Okay, so you're going to have whatever it happens to be. In the case of address 0, you're all going to be zeros. Okay? In the case of address at the very tippy top, 65535, since this would be a 16-bit integer, the address bits are all going to be 1s. Okay, and in between there, you're going to have a combination of 1s and zeros that will determine what address is being accessed by the microprocessor. Okay? Now, why do we need a bipolar prom? Okay, well, there are two ways to do what's called address decoding. Okay, and what I mean by address decoding is the address that comes out of the microprocessor has to be decoded so that the range, in this case, let's just use the first EPROM, from 0 to 7F. Okay, that's only 8 bits. Okay, no, it's not. It's 256, 10 bits, 11 bits. I don't remember. Okay, I'm not just trying to get the point across here. So the range of bytes that are stored in this this EPROM are going to have to be covered by the bits that are set on the first, I'm going to say 11, I could be wrong, 11 bits of the address line. Okay, so what you want to do is you want to have, when those bits are set to point to this EPROM, you want only this EPROM to be active. But what about these lines up here? Okay, you don't want these lines are still going to be active. All right, so these lines, even though they're active, they cannot allow these EPROMs, the other three, to be accessed. Okay, So you want to, quote unquote, decode the ones and zeros on these lines so that the only the first EPROM is going to be active. Okay, well, what happens as the program executes and the address outputs begin to increase, and the address bits, instead of being, the last one is 7FF, and then the next one, you increment by 1, it's going to be 800. So you don't want this EPROM to be accessed, you want this EPROM to be accessed. Okay, so you've got to have decoding circuitry that will deselect this EPROM, select this EPROM, and also deselect this EPROM and this EPROM. Okay, so that way, whatever address is available or presented on the address lines, the correspondingly selected EPROM will provide its data. Okay, because the address lines can only point to one thing at a time. Okay, one byte at a time, regardless of where the byte is stored, what part it's stored in, be it an EPROM or, in the case of a RAM, the RAM is also going to have to be decoded. Okay, the designer has to have some way to select at the appropriate address the appropriate EPROM. Well, you can see here that he's got 4 lines which are going to select one of 4 EPROMs. Okay, so he needs digital circuitry that's going to sit in between the addresses coming out of the microprocessor and the chip select lines that are going into the EPROMs. So only the correct EPROM is going to be accessed. Okay, so that's the problem. Okay, now there were 2 solutions that a designer could use. One would be to have a whole bunch of logic gates. Okay, logic gates are their logic functions like and or, NAND and NOR. Anyway, he could take a whole bunch of these logic gates, which would respond to inputs of zeros and ones. And I'm not going to try and show you how that would work, because it would be a lot of gates that would be required in order to do this decoding. Okay, and there were designs of where they did that, and depending upon the number of gates, it might have been more cost effective to use gates to do the decoding than it would be to use a bipolar prom. But bipolar proms were widely used, okay, in order to do the decoding of the address lines. Okay, so how does that work? Well, a bipolar prom, you would take a bipolar prom if you were a designer, and you would put it in between your address lines. And normally the bipolar prom, as I said, all of the address lines go in parallel to all of the memory parts. Okay, so the addresses are applied to equally to all of the EPROMs, but only the EPROM that's selected is going to give you its output, its data. Okay, so what the designer could do, he could take a bipolar prom, and I don't want to smear my wonderful artwork here, and he would put it in between the address lines of the microprocessor, okay, and the EPROMs, okay? And what would happen is he would program the bits in the bipolar prom so that when a specific arrangement of bits was applied to the address lines, a bipolar prom has address lines just like EPROMs do, okay? But when the corresponding bit pattern was on the address lines of the bipolar prom, then the bipolar prom, let's say that this is a, what's one that you guys might recognize? Let's say this is an 82S129, okay? This is a 256K by 4, Okay, 4 bits. So maybe I picked the wrong one because I don't have another another bit to address my RAM chip. But anyway, so on the output of the bipolar prom, you've got 1, 2, 3, 4 outputs. Okay, and you have, I'm going to erase this here, 82S129. You had something called chip select or output, and it would depend on who made the part, but I'm going to call it chip select. Okay, so you've got address lines going into the bipolar prom here. These guys are going into the bipolar prom. And then you got output lines that are coming out of the bipolar prom. And where do these go? Well, we got one that's going to go to here, one that's going to go to here, one that's going to go to here, to, oops, screwed up. Well, you get the point. Should have put this one down here anyway. So, well, I'll just use this one for my RAM. Let's say this goes up to the RAM part. Anyway, so when the bits that correspond to the correct address for the bipolar into the bipolar prom, that you want the outputs of the bipolar prom to choose the proper EPROM. All right, you can do it with one part. Okay, so where before you were looking at multiple small-scale integrated circuits to do the decoding, now you can say for the bipolar prom, you can say, okay, for all of the bits between, in the combination of bits between 0 and 7FF, okay, then whenever that combination of bits is on these output lines, this line is going to activate my EPROM 0, okay, first EPROM. When I get address combinations from 800 to FFF, any of those that come out of the address lines, I'm going to activate the chip select on this EPROM. And when I get more, you know, up to 1000 to 1FFF on my inputs to my bipolar prom, I'm going to activate this EPROM, and so forth. And the thing that you'll find is you're dividing the address space of the microprocessor, and this was an 8-bit microprocessor. It would have a maximum address capacity of 65535, or they would reference it as 64K. Okay, so the bipolar prom would do the decoding between these address lines, and then when the microprocessor issued its read command, the read command would activate the bipolar prom. It would then decode the proper address and activate the appropriate EPROM, and the EPROM would then give its data back over the data bus into the microprocessor. Okay, so that's basically why these parts were used, and they were great. They were great, okay, because they saved a lot of additional components. But they had one big problem, okay? The big problem was that once you programmed your bipolar prom, it became a custom part, okay? And one of the things that engineers and purchasing people do not like are custom parts, okay? Which means that now, today, you know, let's say you're working on we don't do video games here, but I know how the systems work. Let's say you got a Miss Pac-Man or some other arcade game, and you find that the bipolar prom is bad. And let's say it's an 82S129. Well, you can buy an 82S129, but it's not programmed. Okay, it's not programmed to fit the application. So you're going to have to program it. All right? And in order to program it, you're going to need a bipolar prom programmer. And that's what I'm going to cover in the next part of my presentation here. before I go there, I'll also say that, as I pointed out in this illustration, this is an 82S 129, which is a 256 by 4. Another common one was an 82S 123. Okay, the 123 is an 8-bit. Okay, so it's 32 bytes by 8. Okay, so it's only got 5 input lines, but you got 8 output lines. 4, 5, 6, 7, 8. So you could do additional decoding. The other thing that you could do with a bipolar prom is if you had more addresses that needed to be decoded than you could do with one chip, you could use one of its outputs to go up to another bipolar prom, and it's chip select, and then it would basically allow you to expand. Okay, so that's why bipolar proms got used. Okay, and there were different sizes of bipolar proms. The smallest one was the 32 by 8, okay, which was the 82S 123. I'll just write it down here, 82S 123, or the 74S 188. These are the exact same part. This one is made by Signetics. This one was made by National. Both companies were bought. Okay, but at the time, Signetics and National were the two biggest manufacturers of bipolar proms. And bipolar proms ranged in size from 32 by 8. Okay, that's 32 bytes of 8 bits. Okay, which is pretty tiny. It's pretty tiny. All right, the biggest one, this would be, just say 82S123. The biggest one was an 82S191. This was a big bipolar prom, and it was 2048 by 8. Okay, so you could do a lot more decoding with this than you could with this, but also this thing sucked a lot of current because it was big. Now, different manufacturers got into the bipolar prom business, okay, and the problem with the bipolar proms, another problem with bipolar proms, is that bipolar proms, they all read the same way. Okay, meaning they've all got input lines and output lines, chip select, and all of that. They don't program the same. Okay, everybody, when it came to programming bipolar proms, went their own way. Okay, so Signetics and National had the two most common programming algorithms. But you got MMI, you had, gosh, who else? Anyway, TI, AMD, they all got into the bipolar prom business, and they all chose different ways to program the bipolar proms. Now, you would ask yourself, why would they do that? Okay, why would they go down different paths? Okay, well, I'll tell you why. Because they had different fabrication technologies that they were using. And when you program a bipolar prom, you're not, unlike an MOS device or an EPROM where you're putting charge on a floating gate, and you can do that, you know, by applying a reasonably large voltage, reasonably large, meaning 12.5, 21, 25, and that'll put the charge on the floating gate of the MOS transistor. When you're dealing with a bipolar prom, I have an illustration here which I will show you what happens. Okay. This is this is not a Philips Signetics, but it gets the point across. This is a bipolar prom data book from Monolithic Memories, which was yet another supplier. They're gone. Monolithic Memories is gone. Let me zoom in here so we can get a little bit closer look at this. Okay, what you can see is that we are blowing little fuses in the bipolar prom. Okay, when a bipolar prom fuse is intact, that's this guy here. Okay, the bipolar prom will read this bit as a 0. Okay, once you blow the fuse, the bit will be read as a 1. What would happen sometimes, and it may contribute to failures today, I don't know, was that the fuse would grow back. Okay, there are things that happen at the atomic level that sometimes people can't explain, but sometimes the fuse would grow back. So it's important, you know, when you program a bipolar prom, this particular activity or event, to blow a fuse, even though it's a little teeny weeny fuse, to blow a fuse takes a lot of current. Okay, you just don't, oh, here's 12.5 volts and a 100 microsecond pulse, and I'll just deposit a little charge. No, okay. To do this, you're talking about hundreds of milliamps and a high elevated voltage and enough current behind the delivery of the pulse to pop this fuse and pop it sufficiently so that what you have is a 1 instead of a 0. Okay, and this is why you can't, reuse a bipolar prom, because once it's blown forever. Okay, so that kind of is where I wanted to arrive in my presentation at the bipolar prom technology. And these memories were not small current consuming devices. They would consume significant amounts of current. And as I said, they were the bipolar prom technology, not NMOS technology. Okay, so the next thing that I want to cover is going to be the eprom plus programming system with the AR32A programmer, because with an adapter we support Philips Signetics and national bipolar proms.